All right, so final topic in our discussion of state machine synthesis. So let's go back to that last machine we developed in the previous class. This was a three-state machine, and we noted with three states, two flip-flops would suffice, because two flip-flops, we have, four possible combinations of flip-flop states, and we only need three combinations. But sometimes this question of how many flip-flops we're going to use and what states we're going to use um, to correspond to the different states of the system, there's different ways we can answer that question. And here's something to consider. So we noted in this system that there were only three states, A, B, and C, and we treated the fourth possibility where we had Q1 and Q0 both being ones. We treated that as a state that we did not expect to have happen, right? And so we used a lot of don't cares in our truth table, and that simplified our design and so on. But consider another possibility. Suppose this is some kind of abnormal state which can occur, but we don't expect it to occur under normal circumstances. And so the usual behavior of our system is, go from A to B to C back to A, or hold in a current state based on this input X. But suppose that there is a fourth state in which the system can be in, some kind of emergency state, for example. So when something unusual or unexpected happens, our system is going to go into this fourth state where both of these outputs of flip-flops are 1. And it's not part of the regular behavior of the machine, but maybe, some other part of the system is set up so that if both of these Q's become a 1, then it goes into, some kind of, emergency shutdown mode, or it sets up a notification or rings an alarm or something like that, right? Not an unusual situation. Well, if that's the case, consider what happens when we go from state B to state C. In state B, Q0 is a 1, Q1 is a 0. Now, we built a bunch of circuitry which says, hey, if we're in this state and our input is a 1, let's change this to a 1 and this to a 0. Well, we know that there are, delays in how circuits respond, and eventually this is going to become a 1 and this is going to become a 0, and we're going to be in state C. But before we get to that final situation, there could be a moment where Q1 has changed to a 1, and we are temporarily in this state 1, 1, and then sometime after that, Q0 changes to a 0, and we're in this correct state C. But it's possible that in going from 0, 1 to 1, 1, to 1, 0, we might go through this intermediate state 1, 1. Now, if everything changes at exactly the same moment, we could go directly from 0, 1 to 1, 0. If Q0 changes first, we might go from 0, 1 to 0, 0 to 1, 0, so we might temporarily find ourselves back in state A. But the other possibility is we might temporarily find ourselves in this fourth state, this exceptional state, where, maybe as soon as something detects that we're in that state, it begins a series of events that, involve shutting down the system or something. So it's a glitch, but glitches in state machines, glitches in machines with memory can be more than just, a little blip on an output. They can be something that changes the future behavior of the system. So it can be advantageous to have our states set up in such a way that this never happens. We never go into these undesired states. We neither temporarily jump back to A before going to C, or go into this fourth state before going to C. So one way to help ensure that is to use what's called one-hot encoding. So hot is a term for an output that is, typically 1, but something that is active, as opposed to something that's outputting a 0, which we can consider inactive. It's kind of a casual term. So one-hot encoding means that only one flip-flop would be outputting a 1 at a time. And so with 3 states, we could choose instead to code our system with 3 flip-flops. So here's our state name, A, B, C, and we could make 3 flip-flops, Q2, Q1, Q0. And we could say state A looks like this, state B looks like this, state C looks like that, and any other combination is not a valid state. And if we're in some other combination, we're not going to do anything about it, right? So if we wanted a 4th state, we could encode a 4th flip-flop, Q3, and have that be a 1. And the idea is when we build our logic systems, you know, if this is our current state and this is our next state, well, maybe this will change to a 1 before this changes to a 0. But if we find ourselves in that state, nothing in the system is going to respond to that because it's not a recognized state. The only states that are recognized are the states where exactly one of our flip-flops is outputting a 1. And so this is one way of dealing with glitches. And so let's do one more design example, but let's use one-hot encoding and design a system that will behave in this way, but be potentially more glitch-free. So I'm going to use this for our 3 state names, and we're going to have our single input X. And so let's make a table, and I'll go to a new sheet. And we'll just use D flip-flops for simplicity. So present state and X. So there's our possibilities. And Q2, Q1, Q0. Alright, so here's our set of inputs. And there are other, you know, input combinations of Q0, Q1, Q2. We're going to take those as don't cares. And so we can list our output based on the present state. So our output Z, well, if we're in A or B, our output should be 0. And if we're in C, our output should be 1. And then we can list what the new state is. So again, if our input is a 0, we're in a hold pattern. If our input is 1, we move to the next state. So we can list the next values of Q2, Q1, and Q0. And then we could list the inputs to the flip-flops. And if they're D flip-flops, the inputs to the flip-flops will be exactly the same as what we want the next state to be. And there we go. All right, so it would take, you know, more circuitry, more hardware, but there's going to be a lot of don't cares. Right, so we should list out all the possible combinations of Q0, Q1, Q2, and Z, and we've only listed, you know, 6 out of 16. But for all those other situations, we could make these D inputs don't cares, and you know, glitches can happen in between clock ticks. Right, it's going to take some time to have our circuitry settle down so that we end up in state B, and then everything will be stable. The clock ticks, we move to state C, and during that transition, lots of different things can be happening. But the idea is that our flip-flops, right, we're going to have equations set up that force the D inputs to whatever value we want, so that, for example, we're going to have circuitry saying, okay, this is going to become a 1, this is going to become a 0. That circuitry can take time to stabilize. That's happening between the clock ticks. But when the clock ticks, if the clock activates, you know, D0 first, so that we change from a 1 to a 0, and we end up in the state, you know, 0, 0, 0 for a brief instant, that won't be mistaken as, you know, some other valid state, because our valid states always have exactly one input being asserted. And so what we're mitigating here is the potential for a glitch when the clock has ticked and we're waiting for all of the flip-flops to respond to their new inputs. And if they respond, you know, out of sync with one another, those temporary changes in outputs before everything has changed won't be misunderstood as a valid state. So that's the idea of one-hot encoding, and it's one of a number of different ways that we can try to mitigate glitches. Another thing related to this is the idea of gray code. And you know, when we count in binary, we count like this. So we write down our numbers in the order in which they would be if we were converting to sequential integers. And if we have a system that is, you know, going through a series of steps, and we encode the step numbers like this, this is filled with glitch potential in the same way that our state machines are. For example, when we go from state 3 to state 4, all three of these flip-flops need to change. And it's possible that, you know, these need to go to 0, so maybe this will change to a 0 first, and then maybe this most significant bit will change to a 1, and then maybe that middle bit will change to a 0. So we started with a value of 3, we went to 4, but along the way we also had values of 2 and 6. And these are glitches. And again, this is happening, you know, over a space of some number of nanoseconds, but it's possible that we have something monitoring our states, and if it notices that we're in state 6, you know, some asynchronous system might say, hey, that's an abnormal condition, let's do something. Let's cut the power to the system, maybe. So there's a different way of ordering consecutive binary numbers, and that's to use what's called a gray code. And here's an example of a 3-bit gray code. Alright, so we still have all 8 combinations of 3 bits, but it's a funny order: 0, 1, 3, 2, 6, 7, 5, 4. But what's nice about the gray code is that anytime we move from one number to the next, only a single bit changes. From here to here, there's only this least significant bit changing. From here to here, there's only the most significant bit changing. And so whether things change slowly or quickly, we're going to start off with this value on our counter's output, and then eventually this will be the next value. And it may happen as soon as the clock ticks, it may happen 5 nanoseconds later, 10 nanoseconds later, but we're going to go smoothly from this to that, and there's not going to be any sort of intermediate values that could, you know, cause glitchy behavior. So this is gray code. It's sometimes called reflective gray code, and there's a trick to writing these bit patterns in the gray code order. So let me call this normal binary. I'll put normal in quotation marks. If you want to write consecutive binary numbers, what do? You write a 0 and a 1. That's our 1-bit set of numbers. If we want to do this again, we write a 0, 1, but this time we put zeros in front of the first half and ones in front of the second half. So now we've got all of our 2-bit numbers. If we want to write 3-bit numbers, repeat that. Put zeros in front of the first half, put ones in front of the second half. Alright, if we want to do this in gray code, it's almost the same process. There's one small twist. Start off with our 1-bit numbers. Okay, if we want to write 2-bit gray code, we take this, but instead of just copying it, we reflect it. Instead of 0, 1, we write down 1, 0. And we put zeros in front of the top and ones in front of the bottom. So there's our 2-bit gray code. Now if we want to do 3-bit gray code, we take these 4 patterns and we rewrite them, but we reflect it. Right? We put 1, 0, 1, 1, 0, 1, 0, 0. And then we put zeros in front of the top and ones in front of the bottom. And there's our 3-bit gray code. All right, so that's a way that we can write consecutive patterns of bits with this property that only 1 bit changes at a time. And if we wanted to write 4-bit gray code, we would take this, reflect it down here, and then put zeros in front of the first 8 entries, ones in front of the second 8. So that's just something useful to keep in mind. All right, that is it for state machine synthesis. We'll finish up some problems in the practice problem sets for this class, and then next class we're going to start talking about Verilog, which is a whole nother topic, and hopefully you've already got the Aldex software installed. This came up a few classes ago, so hopefully that's installed and ready to run on your system, or you can use the machines in the Collaboratorium and install the software on those. Alright, so I'll see you next time. We'll start doing Verilog.